Hi, in today's video, we'll be going through invertibility of a function. In the previous video, we have stated what does it mean for a function to be injective, surjective, and bijective. And now we want to state when does a function have an inverse. And so what do we mean by that? Picture this. You have a set X containing A, B, C and a set Y that contains 1, 2, 3. You map A, B, and C by F into 1, 2, and 3 respectively. And now you want to have the reverse arrows pointing. And so you want 1 to go to A, 2 to go to B, and 3 to go to C. And so if you see the picture, now G of 1 is A, G of 2 is B, and G of 3 is C. But what is 1? 1 is actually F of A. And 2 is just F of B. And now you can say that G circle F of C is equals to C. And this is actually just like applying the identity map on A, B, and C. And so because every input now correspond to the same output, these two maps are equal, G circle F and the identity. And so we want the inverse function to be able to go in the opposite direction of the map, original map. And hence, we say that F is invertible if and only if there exists another function such that G circle F is the identity, but it also must have F circle G to be the identity as well. So it needs these two properties to be considered invertible. And we like to note that this inverse is actually unique and we can prove why. Let's suppose we have another function that we call the inverse of F. That means it has the property that H circle F is the identity on X and F circle H is the identity on Y. And so we want to prove that H is the same as G. To be the same function, it means that for all the outputs in Y, G of Y is the same as H of Y. They have the same output. And so, we let Y be an element of Y, be arbitrary. We note that the identity of Y is Y. But we already note that G is the inverse. And so, F circle G of Y is also Y. Because F circle G is identity. Now we apply H to both sides. We get H bracket F circle G of Y is the same as H of Y. By associativity of composition that we proved in 2 videos ago, we now show that H circle F circle G of Y is the H of Y. But since H circle F is the identity circle G will just be G. G of Y is the same as H of Y. And so, for all Y in Y, G of Y is the same as H of Y. And so they are the same function. Hence, because of the uniqueness of the inverse, we can denote it by a very intuitive symbol, F inverse, from Y to X. Some may not find this intuitive, but note that this to the power of minus 1 is not reciprocal, but the inverse. And you just need to read the context to be sure what the author is talking about in the textbook or in the research paper or anything. Now, let's look at a picture to show when it does not have an inverse. Take this example at the top. A is mapped to 2, B and C are both mapped to 3. If you were to reverse the arrows, you will have to say 2 is mapped to A and 3 is able to map to 2 elements now. But we can clearly see this is no longer a function, because 3 is mapped to 2 outputs. so it's not well defined. And the value of 1 is mapped to nothing, so it's not everywhere defined. And so, because of the failure in injectivity in the original function here, the inverse will not be well defined. But also, because of the failure in surjectivity, the inverse function is also not everywhere defined, and hence, it is a fact that if f is invertible, f is also bijective. This example demonstrates why that's so, but an example is just a specific case, and to prove this for all functions, you can do it as an exercise. It is also proven in the book, so you can refer to that for the answer on the proof. But I hope that this picture gives you a better understanding of why you must be both injective and surjective for inverse function to exist. Next, we'll be moving on to the last part about functions, where I'll talk about the image and preimage. So the image set is just a subset of the codomain, but instead now of taking the whole domain as your input, you only take a subset of the domain. And so maybe a subset AB here, you won't get the whole of B, you only get the set 1. And so this is what is written out. So you're not getting an element, but in the end you're getting a set containing the elements in B. And the preimage is the set of inputs that give rise to the output. For example, we take the preimage of 1. A and B both are mapped to 1, so these two will be in the set, the preimage set. But we like to note that f need not be invertible, and because there is no restrictions on whether the preimage can be empty. Because if we to take the set 2 and preimage it, because there is no elements mapping to 2, it just results in the empty set. And so you can see how there's abuse of notation where we still use the f to the power minus 1, but like I said about reciprocal and inverses, you just need to take note of the context to understand what the author is trying to say. And so things to remember is that the image will just be a subset of the range, or a subset of the codomain also, and the preimage will be a subset of the domain. And you just need to think of it as the image as the range and the preimage as the set of inputs that give rise to your output, be it empty or not. And so images and preimages are used very commonly throughout all studies of mathematics, and there are few propositions that we want to prove about them. So the basic ones are how they respect set theoretic operations for preimages. For example, the preimage of a union is just the preimages of each set union together. The proof is as follows, and you can see how it is really just using the definition over and over again, so you can just use a series of if and only ifs and flowing through with the logic of and, or, and whatnot. You can also prove that the image of a union is the same as the union of images. And it is also a good exercise to prove why one inclusion for the intersection holds for image but not the other. So the image of an intersection is actually only a subset of two images intersecting together. Equality need not hold, and you can think of counterexamples to prove it. And so we like to say that preimages behave well under set theory operations, but images do not. Do try out more exercises in the textbook to better understand inverse functions, the image and the preimage. This will play an important role in other fields, as knowing whether a function has a preimage, you are able to do other things about it that is very important. I won't dive deeper into that as it might be confusing, but just note that it's important to understand images, preimages, and inverse functions very well as the previous videos if you have not catched up on those. Thank you for listening, and I hope you have enjoyed this video. Please like, share, and subscribe, and I'll catch you in the other video. Thank you.